Okay, let's get started with the last talk. So we are having fun in the past 2 days, but we are coming to the grand finale, and by one of Hiroshi's contemporaries, Herman Verlinde. Please come.
Okay, thank you. Okay, it's of course a pleasure to be here, and lead on the finale. Apparently, because I'm in the end of the alphabet, but but of course, again, it's a real pleasure to be here, and really. To me, again, Hiroshi has been a friend, certainly for more than half my life. I think indeed we also met indeed in September of 1988 when we arrived in Princeton. So indeed, I'll talk a little bit about my memories, and I call it the journey with Hiroshi, because one of the things that really strikes me, especially for these kind of events. And it's the 60th birthday. It's a round number. It's maybe a reason to have a celebration. But you start recognizing that first when you meet someone for the first time, indeed in this case in Princeton, this is a colleague. Quickly they become friends. But then it's actually pretty amazing to actually think that 34 years later. You're still basically on this journey together. So it's not just friendship. But it's really sort of an experience that you're sharing with people, and Hiroshi has been enormously valuable for me as a friend, as someone who inspires, as someone who gives an example of how to live, how to be a generous human, but also to be a brilliant scientist. So indeed, I'll start with a few memories. Again, when we arrived, again that year, I know actually that David was on sabbatical that year. I was at the I was at the university, but I spent quite a bit of that year at the Institute of Advanced Study, and everything in those days was actually happening in that building here, which was the D building. That's where all the people that we know were writing all those amazing papers. Nati was there, and Edward and Frank Wilczek and others. Actually, the way the offices were not quite correctly identified earlier during Eric's, because I remember distinctly, there was indeed the left, the wing where Edward had his office, and then there was a big office that you shared with Misha Bershatsky. That was sort of on the second floor on the opposite side, and you could call that basically the kids' corner of the. That was the library. Yes. And since I spent sort of quite a bit of time there, but I didn't officially have a desk or an office, again, Hiroshi and Misha were enormously welcoming. It was fun to be in their office. I think I may have at some point just basically decided that one of the desks in their office, because they had a bigger office that they were sharing, was mine. So indeed, I learned a lot from all the discussions at the time. And indeed, even in those days, I would say Hiroshi was already an inspiration for me. So the papers, again, when Hiroshi gave a talk at our Verlinde Fest, he indeed talked about sort of the common interest in chiral bosonization. But during the time in 1988-89, people were studying rational conformal field theory, indeed, aspects of string theory. But I remember in those days, I already started thinking about things like, hey, what would a theory look like if it's not rational? What would irrational theories look like? And then, indeed, there were interesting developments that started to go towards gravity. There was a paper by Polyakov, and then there was this paper that Hiroshi wrote with Misha Bershatsky about the hidden SLN symmetry. Basically, they explained how to connect the Westermann-Witten model to essentially a theory that, already here in the abstract, is called the co-adjoint orbit theory of the Virasoro algebra. They understood how to get the stress tensor and the Virasoro algebra from the Westermann-Witten model. At the time, I was also thinking about sort of the 2+1 lift of this story, and I was interested indeed in what does it mean for a Virasoro algebra to come from 2+1 dimensions. And I had this paper where I studied basically the space that you had to quantize essentially to get the conformal blocks of a conformal field theory in 2 dimensions. this was neat. Basically, these papers were probably at around the same time, although I know that Hiroshi's paper was a bit earlier. And in those days, we already started uncovering actually relationships, and you can read it here, with 2 + 1 dimensional gravity and the Virasoro symmetry. So that was becoming clear. The thing that we didn't know at the time for sure was that there might be connections with black holes. We didn't fully appreciate that, but the geometric aspects of this really have percolated all the way down to sort of developments that have been taking place more recently. Indeed, that sort of indeed nowadays are in the context of holography and ADS CFT, but especially in the example of 2-dimensional CFTs, many of the structures were sort of already emerging in those days. Indeed, let me make another jump. There are many, of course, places where we met. Actually, after this paper, I remember we spent 2 or 3 weeks at Zurich.
Yes, we gave a talk on this.
On this, and that we had very useful discussions at that time, because I hadn't published the paper yet, but I already had the results. But then indeed, quite a bit later, we met in all kinds of really beautiful places. This was actually a workshop on what was it, St. Thomas, this Canal Bay. It was a beautiful place, probably one of the most beautiful places I've been. Again, you could snorkel and you could see the turtles and all the fish swimming around you. And as you can see, here's Hiroshi, as usual, in the middle of the photo, and I'm usually in the back because I'm tall. That's where I am. Actually, this photo was a photo that Hiroshi sent to me, because indeed, when I started looking back at how many photos I have of Hiroshi, they're far fewer than I have than Hiroshi has of me. And we'll come back to that a little bit later. But I should say, again, this was a beautiful conference, not only sort of because of the location. This was like half a year after the AMS paper. Again, here's Joe Focinski. And the discussions there were actually very stimulating. And a lot of the overlap between condensed matter theory and high energy theory, at least you could see already many of the roots happening in that meeting. This was 10 years ago. One thing I want to emphasize is that when I think back of the places where I'm meeting Hiroshi, this is a beautiful place, but I can't think of basically places where I meet Hiroshi that are not beautiful. What about Kyoto in the fall, right? It's beautiful. Or maybe you meet him in the spring in Tokyo. Yeah, I thought, at least since someone mentioned that you probably would want to dress maybe differently on that occasion. But anyway, there you are. But of course, here is really at home in Aspen. That's where we've met many times. I do remember indeed that very first workshop in 1989. One of the things that impressed me immediately about Hiroshi, and everyone will believe me that this is the story, is that he, on the first sort of, he said at some point he comes back and said, "Today I went trout fishing, and I caught enough trout for my family. Do you want to come over and eat the trout?" So clearly, again, Hiroshi was immediately at home in Aspen, and immediately knew how to take take full advantage of being in such a beautiful environment. So again, with that talent, I was actually very happy indeed to know that Hiroshi would come to our birthday party in Amsterdam. I would know that Amsterdam would immediately look beautiful when Hiroshi comes. Here's the photo, and with again the new Minister of Education, a few other people. Here's Kumrun. So that was a beautiful, event. At least the weather was nice, and Hiroshi gave a very generous and talk, and he had quite a bit of information still about myself that I lost track of, including indeed he actually found notes that he had sent himself about the early days of sort of doing calculations in parallel bosonization. But he also showed a photo of me in the meeting on St. John's, so at that point I thought, hey, I have to also take a photo of Hiroshi. I didn't quite have my phone ready in time, so I had to go back in time and take the photo. So this is actually the moment that Hirose shows the photo that he had taken of me, sort of giving a talk in Canal Bay. So I have just a proposal. If I just go like this and you take a photo. Yeah, there's been other birthdays coming up.
I can use this spot your 120th birthday.
Okay, so let's get lead to sort of the physics. By the way, I had indeed a little technical mishap, so I needed to use two files.
Right. So now it's the time to switch.
Yeah, now's the time to
Okay.
switch.
Yes.
So now we get to the physics.
Yes. So bear with me a few seconds.
So that I'll start indeed just by discussing. Basically, I'll discuss a little bit of things. Let's call them food for thought, or maybe it's thought just before food. And it's inspired indeed by again the ideas that Hirose started. And the first part of what I'll talk about is very directly linked indeed with this paper that I mentioned that connects the geometry of the Virasoro algebra to the Witten model and to essentially 2+1 gravity. And again, nowadays, again, when we talk about conformal field theory, indeed, thanks to the ADS-CFT correspondence, we think about indeed gravity in one more dimension. Let's see if this actually works.
Is it not
I think I
working?
pushed that
Okay.
button.
Yeah. Okay. Yes. Yes. Is it working now?
Yeah, no, it's
Okay. Good.
So, so the first sort of topic that I want to briefly sort of discuss is that often indeed we're interested in black hole entropy, and black hole entropy is often thought of as something that's literally hidden inside of the black hole horizon and something that's inaccessible to the outside. But precisely the structure that basically was uncovered in those papers that I mentioned in the late 80s. Actually indicates that a lot of the entropy of the black hole can actually be understood purely on the basis of geometry. Indeed, the action that Misha and Hirose derived actually is able to describe the Virasoro representations, indeed the Virasoro algebra, but the motivation of actually lifting it to one more dimension is to also understand not just the symmetry algebra, but also the space of representations and actually counting how many representations there really are. And so this geometric description is actually already able to uncover a lot of the actual, the amount of entropy that a black hole can carry. And one way of seeing that is as follows. So there is indeed a standard description of a black hole in 2+1 dimension. That's the famous BTC black hole. If you make those numbers T constants, then this is actually the BTC black hole metric. But there's a more general set of metrics where you basically make those functions TU and TVV functions of these coordinates U and V. And essentially they're given indeed by the Schwarzschild derivative of those functions big Q and big P. So basically the space of black hole metrics in 2+1 dimensions is actually parameterized by two functions. And if the boundary of the ADS space is a circle, those are two elements of what's called DFS1, which is precisely the variables that Hirose and Misha were studying. So indeed, what we could do is we could actually look at the space of all solutions of this type. And just a way of visualizing it is that if a black hole is a round thing, which is normally what we think of, then this is sort of a gauge choice, because this is called basically the unique black hole. That's the black hole with no hair. But then what happens, you have boundary gravitons, we think about them, they'll wiggle the boundary. Or you can go to another coordinate system where you make the boundary a perfect circle. But if you make the boundary a perfect circle, the black hole horizon wiggles. So what you could do is you could do both. You have the boundary circle and you have the black hole circle, but then you have a transition function. You have two coordinate functions. So there's a diff S1, two diff S1 degrees of freedom in those coordinate patches. And often people sort of call these things the boundary gravitons. And those boundary gravitons are not thought of as being necessarily essential for the black hole entropy. But let's actually see if that's true or not. And I'll explain it in a moment why initially people might think it's not. But anyway, the mass and the angular momentum are related to the contour integrals of these stress tensors, which we can write like that. And now we can ask a question. Suppose I take the volume of a thin slice of the phase space of this particular black hole geometry, where I specify that the mass and the angular momentum is within a certain thin sliver around a given mass m and j. Now I'm going to take just the classical phase space volume of that particular slice. The fact that I'm doing phase space physics means that I'm essentially sending h bar to 0, which means c to infinity, which means I want to keep this quantity finite, which is the black hole entropy. So I'm sending these combinations to 0 with that thing finite.
Both or one of them?
I send both of them to 0 so that the total black hole entropy is finite in the c to infinity limit. I have a proposal, or you can call it maybe a conjecture, but I think there's quite a bit of evidence for it, that this classical volume is actually equal to e to the power of the entropy of the black hole. So this is classical information that sits outside of the black hole. It has a phase space volume, which I would not, according to WKB, indeed associate with an entropy, and it's going to be the black hole entropy. But basically, by taking this limit, let me emphasize that the fact that m plus j goes to 0 means I'm going to be looking at the spectrum that's still part above c minus 1 over 24, but it's the spectrum that sits just right in that range. Now, it happens to be that this particular limit is precisely the limit that reduces this coadjoint orbit theory of the Beer-Zor algebra to the Schwarzschild quantum mechanics. This is precisely what this limit does. And indeed, it's not entirely surprising, because basically, if I want to fix the value of m plus j, since m plus j plus or minus j was the contour integral of the Schwarzschild, if I indeed basically start integrating over the volume of all the possible diffeomorphisms, and let's first do it in a canonical ensemble, it turns out that at that point, you just get the Schwarzschild quantum mechanics partition function, just identically on the nose, because I'm just doing the integral with the Schwarzschild action. And this is the quantity that one can compute. And actually, the way to compute it is precisely, at least one way to compute it, is precisely to study this particular limit of the CFT partition functions. And indeed, if you take that particular limit, you recover the usual formula for the Schwarzschild. And indeed, you recover also the fact that the entropy that the Schwarzschild quantum mechanics has indeed behaves like e to the power the squared of the energy. And that's precisely the thing that matches with the black hole entropy. So it's still, so as I said, this is food for thought. It basically means that if you even just look at a classical information that sits outside of the black hole, there is information in there that actually extracts at least a formula that hints already at the Bekenstein formula. So this is something that follows indeed from the geometry of 2 + 1 gravity. You could say, hey, that's very special. It's true that actually, even if you do black holes in higher dimensions, this is actually a figure of a paper that Sergio Kleinemann actually sent to me over the weekend. They're doing stability analysis of Kerr. And even if you take Kerr solutions, they're all the same kind of wiggly solutions of waves around that. And indeed, the way they prove stability of Kerr, they do exactly the same thing. They basically split up the space-time into sort of these different layers where they indeed allow for diffeomorphisms, and they do a reframing in order to basically go to the no-hair frame. But there's again basically a set of diffeomorphism modes that's being trapped around the black hole.
900 pages.
Actually, the email said, here's a nice summary of the paper. I can send it to you. It's 38 pages. 38 pages. So 900 pages is what it requires, and it means that there's a lot of structure associated with classical solutions of black hole. Yeah, and most of that structure is actually outside of the black hole. Okay, so that was one of my sort of food for thoughts topics. Let me discuss another one. This one will have some formulas, and I'll take at least philosophy that formulas don't count. So just listen a little bit to the storyline, and at the end there will be again a little bit of food for thought. So T.T. Bar deformed conformal field theory is actually also partly inspired by the same kind of geometric picture of the relationship between gravity and two-dimensional conformal field theory. And Samolojkov and Smirnov wrote an amazing paper going back to earlier work by Solomon Lojkov that showed that this particular deformation, if you turn on this T.T. Bar coupling, is actually sort of an integrable theory, or this you can compute many things from it about it. And in particular, they derived this particular formula for the deformed energy. And then later, soon after that, people studied basically the partition function that you get. If you just take the CFT partition function and you deform the energies with this particular T.T. Bar coupling lambda, you plug in this formula in the partition function, and you actually get a modular invariant object, which of course seems maybe automatic, but actually turns out that this is the only formula that you can write down for the formation of the energy that keeps the modular invariance. But it indicates that basically there's a path integral definition of the T.T. Bar deformed theory. And indeed, what you can do is you can take a CFT and you can couple it basically to a two-dimensional sigma model that just maps the worldsheet or the place on which the CFT lives into a two-dimensional target space.
10 minutes.
Thank you. Or another way of saying it is that there's a particular kernel that you can take that you can use to integrate here against the CFT partition function. You integrate over that kernel and you get this particular T.T. Bar deformed partition function. But that kernel and this integral, which at this point goes over the full upper half plane, can be repackaged in a way that makes it a little bit more geometrical. Because the CFT partition function is modular invariant, it's natural to fold this thing up into something that's also modular invariant in terms of tau. So by the way, in this particular equation, this is the shape of the CFT torus. This is the shape of the T.T. Bar deformed CFT torus. So indeed, you're transforming from one to the other. And this rho 2 parameter is actually the T.T. Bar coupling. It's related to the T.T. Bar coupling in this particular way. And for people that know a little bit about this two-dimensional free field theory mapped to a torus, if you indeed sort of do this particular folding trick where you allow yourself to basically sum over all the modular orbit and fold this Gaussian expression into a modular invariant expression, you actually discover that you basically are just computing the partition function of a free boson. But basically a partition function of a free boson that maps the worldsheet torus to the target space torus, but with wrapping number 1. That's the restriction. And that's a way of understanding the T.T. Bar deformed partition function. So one question that we started discussing with a number of collaborators is what would happen actually if you sort of allow other wrapping numbers? Now, let me give you another motivation of the same, that leads actually to the same structure. So before discussing the other wrapping numbers, if we do holography, we are interested in two-dimensional conformal field theory. And one of the reasons why we're studying two-dimensional conformal field theory is because as an ADS-CFT system, is because of going back to the Stromer-Gervatha or the D1, D5 bane system, or indeed ADS-3 with the long strings that indeed Rossi and Juan studied. you have basically what's called an asymmetric orbifold, where you can have winding numbers of the string. So it's at that point it turns out to be natural, and it's a sort of mathematical object, if you wish, or you can call this the grand canonical partition function, where this Zn, I didn't write down the equation, is the partition function of the n-fold symmetric product of a certain CFT. Oh, there we go. And then indeed, there's basically a formula for a CFT with a symmetric product target space, which you can think of basically as this looks like a second quantized partition function. And indeed, that's what it is. This is a second quantized free string theory based basically on the CFT that you have as being your transverse directions. But now let's TT bar deform it. Okay. We're going to basically choose a particular type of TT bar deformation. So here we're deforming the energies to deformed energies, but it turns out that you have to rescale the TT bar coupling a little bit because of the fact that you can have these higher wrapping numbers. So this is just a way of a la Smirnov-Samolotchikov guessing what the TT bar deformed partition function is. So let's take this thing as an example. It turns out that this thing has amazing properties. Basically, what I'm going to show is that this thing, not quite this thing, but a very natural extension of this thing has an S-duality symmetry, meaning the following, is that this thing is going to be symmetric under the interchange of sigma and rho, and it's going to have the full duality symmetry under SL2Z transformation from rho. That's a mathematical fact, not quite for this formula yet, but for another object. And let me actually build in the other object sort of by construction.
5 minutes.
Thank you. So what I'm going to do is I'm going to study indeed another partition function, which is defined as follows. I'm going to specify what its free energy is. And the free energy is given by taking the CFT partition function and integrating it against the Narayan kernel, Narayan partition function of mapping a torus to a torus. So this is now my target space torus, and now I'm going to sum over all the wrapping numbers and all the winding numbers. Then I know that this thing is going to be invariant under the T-duality group. And I should have set the metric on this particular torus. I had it on a previous slide. And it has a certain ship. Here it is. And the size modulus sits here. And we're also adding a B field. And it turns out that the B field is precisely this quantity here. So the chemical potential, the symmetric product, turns into the B field. And the TT bar coupling is the other, is the size of the torus. And this Narayan sum has, again, amazing properties. It turns out even that this Narayan sum is even triality symmetric, where you interchange all the three parameters, tau, rho, and sigma, and it has indeed these duality symmetries. So by construction, this particular object has the symmetries that I mentioned. And indeed, you can do the computation. You can compute the object. And the object indeed will look like the expression that I wrote down for the TT bar deformed symmetric product, CFT. But it has indeed one extra prefactor. And the extra prefactor, basically what it corresponds to is the wrapping number 0 sector. So what you do is it's the partition function, it turns out to be the partition function of basically the scalar particles, the scalar states in your CFT. So you have 1 minute left. Is that correct? Yes. Let me just list the remarkable properties that this thing has. And it's symmetric under, you don't see it in the expression, but by construction, it's symmetric under the interchange of rho and sigma. You can call that mirror symmetry, because rho is the size modulus and sigma is the shape modulus. It has an S-duality symmetry, meaning in the TT bar coupling. I can do this transformation in the TT bar coupling, and it's invariant. It turns out it also has a spectral symmetry. If I apply the Laplacian on the fundamental domain on rho, I get the same eigenvalue, but it has the same value as applying the Laplacian on sigma. So this F actually is diagonal in terms of eigenvalues of the Laplacian on the fundamental domain. There are these beautiful operators called Hackey operators. They also act diagonally on this thing. And again, there's this bigger univalue. So this is just food for thought. Question: what does this object mean? And basically, what it kind of says is the following: is that basically by the TT bar deformation, we've actually introduced a scale. The dual theory was ADS3, but there was a torus hanging out there somewhere. And if there's a torus and I'm doing ADS-C of t, then the torus doesn't introduce a scale. It's a target space torus, and it has been shrunk to 0 basically in the decoupling limit. But as soon as I introduce a scale, I actually know that my theory is a string theory, and the string theory should have then the full duality. Okay, no more conclusions, except, of course, again, happy birthday. I'm not going to try to compete with how I pronounce this. I think previous speakers have done this. Happy birthday, Hiroshi. And it's been a wonderful to be, again, your colleague and friend. It's been a wonderful 2 days. And I also want to thank Masahito for bringing us here and for being part of this celebration.
So, so I have a question about the earlier part of it. So you said that there is a standard argument that the boundary graviton will not be enough to count the number of states, and so usually one of the standard arguments is that for large central church, the number of states that Virasoro descendants counts is like equivalent to C for 1.
Correct.
So your calculation is different because either volume calculation is different from the standard counting, or the limit is different.
No, so you're correct. So if I take indeed any given state in this very dense spectrum, although it seems that there are more descendants than primary fields, but if I sit at a given energy level, the primary fields dominate. And then you're right that the Virasoro descendants are very subleading.
Right.
But the thing is the following: is that this particular functional, this particular definition that I'm taking here, so I'm taking the volume where I'm allowing the mass and the angular momentum to be shifted within a certain small range. So I'm not literally fixing the value of these contour integrals to an exact number. By the way, your formula with Daniel, where you count the dimension of the hair with the discrete symmetry, has the dimension of the representation and the multiplicity of the representation in that formula. So it turns out that in this case, also you do basically the same calculation, but for SL2R. And what this integral actually here does, it basically knows about the density of the representations. Another way of seeing it is as follows: is that in this limit, and actually beta also takes a particular limit, you project on the identity character in one direction. But it turns out that you're actually measuring the spectrum by doing an S transformation, where the identity character, you're basically doing Cardy's for calculation. So this partition function picks up the Cardy's factor. Now it's a little bit surprising because there's no Planck's constant. I basically sent Planck's constant to 0, Planck length to 0 in this limit, but I can still do that indeed by zooming in on this particular lower band, and that's exactly the band that the Schwarzen quantum mechanics, where the Schwarzen quantum mechanics lives. So you get more than just the Virasoro descendants. You get also the density of representations.
Okay, more questions? Okay, if not, we can have the discussion afterwards, and the next time.